Okay, so dear members of the ProISSI Association, dear colleagues, dear friends, I think we can start. It's my very great pleasure to welcome you this evening, this big audience here for a talk about extrasolar planets. As to be expected, this seems to attract a lot of people, and obviously when looking at the news, what is ongoing on all this research that is taking place, and it is my very great pleasure that I can introduce to you this evening Professor Christoph Mordasini, our tonight's speaker, and I would like to give you a brief outline how his path in exoplanet research has been evolved in the last couple of years. And I start really with the school time of Christoph, because Christoph is coming actually really here from Bern, and he also did the school in Bern, so he was at Gymnasium Kirchenfeld, Typus B, I've heard, which is most amazing that nevertheless he then decided to go to science and physics. So he decided to study at the University of Bern, where he started undergraduate studies towards exoplanet research. He graduated there with a master's thesis on planetesimal impacts into forming giant planets under the supervision of Professor Willy Benz. This is on theoretical work, but nevertheless, Christoph was always also very much interested in observational work and generally in astronomy. I met Christoph personally the first time when he did the famous Astropraktikum, where I was a supervisor, and Christoph was a very eager student. Eager to learn a lot, and of course he did. He also was involved in Zimmerwald, where he got my successor as a night astronomer. That's what students usually are doing when they have to earn some money, so that's a typical thing. But nevertheless, he was very successful. After having successfully defended his master's thesis, he continued PhD research at the same institution. He graduated there with a thesis on extrasolar planet population synthesis, again under the supervision of Professor Willy Benz. And during all this time, he also did observational work in La Silla, I think. So I read in your CV that more than 100 nights or so you performed there and did observational acquisition of observations, which is a very good mixture of theoretical work and really doing observational work, which not so often the case, I would say. He then moved on as a postdoctoral researcher to the Planet and Star Formation Department of the Max Planck Institute for Astronomy, where he headed towards habilitation that he obtained eventually in the year 2013 in the Department of Physics and Astronomy of the Karl Ruprecht University in Heidelberg. And then 2 more years as a PD, as a Privatdozent there, until he eventually returned to his roots, to the University of Bern since 2015 as a group leader of the Swiss National Science Foundation starting grant project Planets in Time, again at the Physics Institute. And I think this grant, it's actually an ERC grant, if I understood it correctly, which was then maintained by SNF during the time when Switzerland was not fully associated to the European research programs. So you see, all led to exoplanets in the career path of Christoph, and we are looking forward very much to tonight's talk about extrasolar planets, a laboratory to confront the theory of planet formation with observations. The stage is yours, Christoph.
So good evening. Thank you very much for the invitation. It's a big pleasure to be here. Thanks also for the introduction. Yes, it's interesting. I mean, thanks to him, I kind of started my observation part of the work, because I replaced him observing in Zimmerwald Observatory, and later on, an observer from Bern was looked for to go observing in La Silla. And I think in the physics department, most people did not do direct astronomical observations except me. So therefore, I could then go to La Silla, connecting theory and observation. And as you can see from the title, this is still one of my most important research points. So let me introduce to you the contents of today's talk. So I will start with an introduction and something on the planet formation paradigm as we understand it nowadays. Then we will talk about the revolution we have seen in the last 20 years in exoplanets. The big interest in this subject was mentioned. We'll talk about observational methods and results. Then we will move more to the theoretical part, because as you could already see in the abstract, if there is one word that characterizes the extrasolar planets, it's really diversity. And here I would talk a little bit how we can simulate this diversity. Then we will come to the main part of the talk, and this is how we can use exoplanets really as a laboratory to overthrow what we have kind of thought what is ground truth when it comes to planet formation theory. We'll see that this was actually not really the end of the story, and we were able to understand that from comparing our theories, which were derived mostly from the solar system, with the observation of extrasolar planets. And in particular, we will concentrate on close-in planets, hot Jupiters, then on the outer limits. So at what distances, out to what distances can planets exist? And then we will also talk about different planetary types. And then finally, I will give you an outlook and the conclusion. But let's start by putting this talk a little bit in the bigger context. I mean, the bigger context is certainly the interest of having on one side our own solar system, our own star, and what is out there in the galaxy, in the universe. If we go first to stellar astrophysics, which is compared to extrasolar planets, a much older discipline in astrophysics. Of course, here we have had first the study of the sun for many centuries, but of course also the study of the stars. And from that, we have had really the fundamental insights in how stars function, things like the Hertzsprung-Russell diagram. So if we can classify stars according to their evolutionary stage, we understood about nuclear fusion as the power or something like the stellar mass function. And these insights that we get here from the stars have, of course, also fed back on the understanding of our own sun. Similarly, we have seen something similar here when it now comes to planets. The planets in our solar system were also studied for a long time, but only for 2 decades we have had this study of the extrasolar planets. And this also has brought to a lot of insight, let's say, for the formation in protoplanetary disk, the accretion of solids and of gas, orbital migration. And this also has then influenced on how we understand the formation of our own solar system. And if we now move into the future, I think there is certainly also a part which is probably a reason why this is such a fascinating theme. We have, of course, here on the Earth, we have terrestrial life, and we are investigating how did it arise. And it's probably exceptional that we are in the position that we are the first generation of human beings, which have, maybe in 20 years or so, the possibility to the technology to also detect whether there is maybe life around on other planets. And this, of course, would then also produce a whole new perspective when it comes to life, like where does life exist, the habitable zone, what are the biomarkers, what is the emergence of life, and maybe is there even complex life? And this will, without doubt, also influence a lot how we understand ourselves as human beings, I would even say. Good. Now, let's focus a little bit more on planet formation. If we want to be mean, one could say planet formation is just a byproduct of star formation. And actually, it's kind of a byproduct because angular momentum is conserved. If we have a collapsing cloud core of which a star is forming, then this cloud usually rotates a little bit. And so it doesn't collapse into one point, but it collapses into the star. But a lot of the material is falling onto a protoplanetary disk. So if you have here a star-forming region, a very big object, then we have a collapse. Part of the gas is falling here into the protostar, but the rest is falling here into this protoplanetary disk. And this is then where the planets form. These disks are typically optically very thick, so we cannot just see into it. And this is a little bit of a problem, because what we have is here, okay, we know that planets are forming in these disks, and we kind of now have an idea, at least here in the solar system, what is the outcome. But in between, it's really difficult to directly observe this process. So what we are dealing with here to go from these objects to these objects are mostly theoretical ideas. And then what often comes to my mind is this cartoon that you have maybe seen, where some theoretician is showing to the other one his derivation of a complex theory. But maybe, yeah, what happens in one step, in this step from going to the disk to the final planets, that, okay, a miracle occurs. And we will see that this approach, just from theoretical points, has really had some problems. And this is, I think, a very fascinating part. We will see in this talk that thanks to the extrasolar planets, we could, I think, significantly increase our understanding of this step. And that's I will discuss at the very end. In the last maybe just 2 or 3 years, a new development has also started, which is the possibility to observe planet formation as it happens, so that we don't have anymore this situation, just the initial conditions and the end product, but that we really see also what is going on here. The study here of the planet formation, our fundamental understanding of planet formation, is of course not something which has just started with the discovery of exoplanets. This is an old discipline. People have been, Kant, for example, has been thinking about how planets form. And the observation constraint we had at that time were, of course, the planets of the solar system. And if we look at our 8 planets and all the minor bodies, there are a number of really zero-order constraints which have led to the basis of our planet formation theory. And the first one is that, as we all know, that planets in the solar system move on prograde, nearly circular and nearly coplanar orbits. Second, there is a certain sequence of what kind of planets we have. And it seems not to be random. And we will see how this has influenced very much our planet formation theory, namely that we have in sequence in order of increasing distance, you have the rocky planets, Mercury, Venus, Earth, Mars, then the gas giants, and finally the ice giants, which are mostly ices and maybe 10% hydrogen helium. Here, we don't have any hydrogen helium. These objects, in contrast, are maybe 90% hydrogen helium, and these are mostly ices and then 10% hydrogen helium. We also note that here, inside of Mercury, in our solar system, there is no planet inside of 0.4 AU. And also, the largest, Neptune, has a semi-major of its axis of about 30 AU. These things were all thought to be major constraints for the planet formation theory, and we will see later that especially these points, but also this one, was a little bit misleading. The way we can have a good overview of these fundamental constraints is have a look at the mass distance diagram. The mass distance diagram is seen by many as something like the equivalent of the Hertzsprung-Russell diagram. So the Hertzsprung-Russell diagram for stars orders stars in terms of their luminosity and temperature and gives a lot of information about the status and, for example, the mass or the age of a star. And if we want to classify planets, what people typically do is to classify them here in the semi-major axis, Venus, Earth, Jupiter, Saturn, Uranus, and Neptune, and here the mass both relative to the semi-major axis or to the position of the Earth and the mass. These are the observational constraints we have. There are, of course, many more in the solar system, and these are just a few illustrations of that. I mean, we have many centuries of solar system studies. Also here in Bern, we have a long tradition of studying all kinds of detailed constraints from the solar system. Here, this is Jury, of course. This is an image from Mars. Here, a meteorite. This is Juno that will measure soon the heavy element content, the composition of Jupiter. We have also the rovers. I think this is, I'm not even sure, I think it's a moon. Titan, or then also the numerical simulation. And all these constraints that we have here have led to our modern paradigm of planet formation. And this is the idea that we can simplify the picture by going in steps. So everything starts, of course, by the star and its protoplanetary disk, where we just said before that this is a consequence of the angular momentum conservation. And the whole process is then a growth from small to big scales. So we start with very small micrometer-sized dust. That's something we also have in the interstellar medium. These objects then grow via sticking to form planetesimals, kilometer-sized objects. These kilometer-sized objects start to interact gravitationally, they collide, form protoplanets, and some of these protoplanets become so large during the presence of the protoplanetary disk that they can attract gas. We form something like Jupiter. And the typical timescale is the lifetime of this protoplanetary disk, which are a few million years, maybe 10 million years in the maximum. So this means that the bigger planets actually are thought to form earlier than the terrestrial planets, because what happens to the remaining planets, which did not accrete hydrogen, helium, they will continue to interact gravitationally, undergo a series of giant impacts until the system has settled into a state which is more or less gravitationally stable, so to form the terrestrial planets on a timescale of maybe 10 to the 8 years. And then finally, in a process which is actually still ongoing, these objects, they interact and undergo dynamical rearrangement such that the timescale on which the instability occurs is comparable to the lifetime of the whole system. This is a nice illustration, but actually it is a very challenging thing if we want to describe that with more than just some nice pictures. The reason is that, imagine what size we are dealing with. This is micrometer sized. Jupiter has a diameter of 70,000 kilometers. These are many orders of magnitudes. So we need to follow a huge dynamical range in sizes and masses. Similarly, also at the time scale, we need to simulate. If we want to put that in a computer, you would have to follow 10 to 8 years. You cannot even do that if you want to integrate simply the universal law of gravity from Newton. It takes too long in the computer. There is a lot of physics involved: gravity, hydrodynamics, magnetic fields, radial transfer, and so on. Finally, there are strong nonlinearities and feedback mechanisms. And this makes this subject, on one hand, very interesting, but it also makes it very challenging. But let's go back to our plot here of the solar system, mass versus distance. And so 2 points I already mentioned, or 1 point that I already mentioned was here. And we will focus on that later on in the talk. So let's talk about here this fact that in the solar system, there are no close-in planets. And the explanation we will have a detailed look at later is the lack of solids that are formed, that are thought to exist there. Therefore, we cannot build any planets at this distance. Then second, we don't have the far planets, and this has something to do with the time scale to grow planets. And finally, we have these 3 different planet types: rocky, gaseous, and icy. And this has something to do with the thermodynamics and the gas accretion physics. So it was long thought that this is by no way just a coincidence, and we will understand later why that we have these 3 points, but that it's rather a necessary consequence of the physics that govern planet formation. So, yeah, because this is it's just it goes not low enough in mass. That's the reason. Otherwise, we would end up with too many orders of magnitude. But you're, of course, right. We have not in any way wanted to exclude these objects. They are also very interesting objects. Mercury, for example, with the high iron content is very interesting. But this is just because it has to do that the exoplanets, as we will see later, we cannot probe yet to such low masses. That's all. That has no deeper meaning. Okay, so let's continue here. So we have these 3 classical predictions. And this was, yeah, I would say already quite a sophisticated theories in the 90s. Most of the work was done starting in the 60s, 70s, Savronov, and so. And then there was the detection of the extrasolar planets. The first one in 1995 by Michel Mayor and Didier Queloz. And of course, a satisfactory theory should, of course, not just explain the solar system. It should as well explain the extrasolar planets. And that's what we can do now that we have all these extrasolar planets. Let's try to put our theory to the test, looking in particular on these 3 points here. So the absence of close-in planets, the absence of planets at large distances, and finally the fact that there are 3 main types of planets. So we can again go back here. This was before 1995, and then there was the first discovery, and yes, that's where it was. 51 Peg is a hot Jupiter, so it fell exactly into this place where the theory predicted that there should be no planets. And you can say, okay, maybe this is an oddball, but history showed otherwise, because if we continue, there are already much more, 96, 98, and you see all these close-in planets here building up. okay, our second prediction was that there is no planet outside here and that there should be more these nice types. But okay, this was already, you see here back in 2007, we had the discovery of these planets at large distances. So you can see also this prediction actually was shown to be completely wrong. And now that we are looking at this large population of all these exoplanets here, you can also see that this grouping in distinct types is not at all realized in the extrasolar planets. You see, you have a continuity from masses here to, we don't, okay, one point I need to mention, this diagram is also strongly affected by our abilities to detect certain planetary types. For example, one thing that is very important to understand, that the fact that we don't have planets here in this regime does it by no means mean that there are no such planets. We just cannot detect them at this moment. But what you can see is that we have both all these close-in planets, we have these planets at very large semi-major axes, and we have here a kind of a continuum of all kinds of masses between terrestrial planets up to giant planets which are even much more massive than Jupiter, up to the deuterium burning regime. So if we just confront again these things, we see that we really seem to have a serious gap here in our understanding that we have derived from one example. I mean, we always know that, right? If you have just one example and then you extrapolate more or less constant, this is never a good idea. And this is, by the way, also, we talked a little bit about life earlier. This is the situation we are in right now when it comes to the search of life. Right now, we have just one example. And this means that what we are looking for is our analogous life to us, because that is what we have. And that's what we are looking for. Maybe when we look at that, we should be ready to also see a lot of surprises, maybe also when it comes to life. Good. Let me, in the next few slides, tell you a little bit how it came that we, from the observation point, how we could detect all these extrasolar planets. But first, what is the current status? I looked at that a few days ago, and nowadays we have around 3,500 extrasolar planets, and they were detected by different methods. To quickly have a look at them, this is first the radial velocity method, then the transit method, the direct imaging method, and then two other methods down here. First, the radial velocity method. This is the type of observation that we do in ISSI. The principle is not complicated. As we know, the sun is together with the planets, they're all orbiting the common center of mass. This means that also the star is moving a little bit, although not much, of course, because its mass is so much bigger than the one of the stars. But this means that if we look on the line of sight, the star which has a planetary system is periodically moving away and towards us, from us and towards us. And this, of course, leads via the Doppler, the optical Doppler effect, to a shift of the spectral lines. And if we have a high resolution spectrograph, then we can measure the radial velocity of a star relative to us as a function of time. And if you find such a nice signal, you can fit an orbit into it, and you can see from the amplitude or from the duration of one orbit how large or how far the planet is. And this is something we do here in ISSI. This is, by the way, very challenging. If you look at the sun a little bit closer, the sun is, of course, by no means, or stars in general, not something really calm or something. They have activities, they have spots. And what we measure here are really very tiny things. So we are talking about meters per second. And for the Earth, I think the amplitude that the sun has, it's the velocity, excuse me, because of the Earth is about 8 centimeters per second. So it's really tiny. We need to measure that despite the activity of the star. But going down to 1 meter per second is actually possible nowadays. This is the first technique. The second one which is also very important, is the transit technique. The transit technique is, to some extent, even much simpler than the radial velocity technique. All you need, in principle, is to stare at stars and follow their photometric brightness. Because, of course, when the star is occulted by a planet seen from us, then the luminosity will decrease a little bit. The problem is, of course, that the degree of this darkening is very small. Now, that's just because it is proportional to the ratio of the planet the radius of the planet divided by the radius of the star to the second power, the ratio of the surfaces. And Jupiter is 10 times smaller than the Sun, so it's a factor 100. It's 1% change in luminosity. And the Earth is just, again, 10 times smaller than Jupiter. So we are dealing with just 0.01% change in luminosity. And this is very, very hard. And this is because why this is simple in theory, but difficult in practice. And because if you want to measure the brightness of a star in time so accurately, this is really hard because we have the atmosphere, we have the drift of the detector and all these things. So this is actually when we then want to go to detect really small planets, what we need to do is to go to space. And I guess many of you have, or all of you have heard about the Kepler mission. This was a NASA mission, which has really revolutionized our understanding of planets, at least in transits, because it has detected something like 4,000 or so candidates. Here you see orbital period versus the size of the detected planets, and you can see here, this is one Earth radii, this is the radius of Neptune, the radius of Jupiter, and you can see all this detection here. And this is a very important constraint now for the formation theory. Good. The last method that has become very important just recently, I would say, maybe in the last 5 years or so, is direct imaging. So the methods we talked about before, you have seen these were indirect methods. We didn't get direct light from the planets themselves, but we detected them thanks to their influence on their host star. For direct imaging, that's different. Here we really take basically a photo of the star, and if we try to detect the companion. Here we have also some difficulties, because you can think that if the planet is maybe few AU from the star is several parsecs away, so the angular distance is just 0.01 or 0.1 arc seconds. It's very tiny. And compared to that, the seeing, so how well we can resolve two objects on the skies because of air turbulence, is rather something like 0.5 arc seconds. So what we need to do is to correct for these influences by using adaptive optics, so to correct for these disturbances due to the atmosphere, to the terrestrial atmosphere. The second thing is that planets are, of course, much less bright than host stars. And this means that they're about, in the infrared, maybe 1 million times less bright than the host star. So what we need to do is also to be able to detect something very, very faint close to something very, very bright. And one possibility to do that is to use a coronagraph, so to block the light from the star. But what is then fascinating in this case is that we get photons directly from these planets. And we talked about this possibility to maybe at one point detect life. And here we have the possibility to obtain a spectrum from the atmosphere of these planets. And this could tell us how this atmosphere is composed. This is an example. This is the most, I would guess, one of the two most important examples of such a direct imaging. So here you have this host star, it's blocked out. Here we have Beta Pictoris B. This was the first observation back in 2003. I know the observers at Marie-Lagrange, they continued to observe it, and it was no more there. They were quite concerned about it. What had happened, was this a false positive? But what actually happened is that 6 years later, the planet reappeared on the other side of the star. While it was here, of course, we could not detect it because it was behind the star, so it was not visible in the glow of the star, but here it is. And this is the comparison here. So we just saw the orbital movement. This is the comparison to the orbit of Saturn. It's about at the distance of 8 AU. This planet is different from what we know in the solar system in the sense that it's still very young, and therefore it emits a significant amount of intrinsic luminosity. What you see here is the infrared radiation that is originating from the planet itself. What this means is that thanks to these different methods, we can probe different parts of this mass distance diagram. And these were actually the colors that you saw before. Red is our detections made by the radial velocity. See, it's relatively close, but also let's say intermediate distances, but it's biased towards massive planets, although we can now detect also these low mass planets, then transits are strongly biased towards the detection of closing planets just from the probability, the geometric one, to have a transit. Direct imaging is the opposite. Here, it's of course easier to detect the planet if it's further away, because we are not so close to the bright star. And finally, here we have also microlensing, which is another technique. You can see this diversity here in the mass distance diagram, but actually that's not the only one where we have this very large diversity. We also have it here. This is the eccentricity, the measured eccentricity as a function of the mass of planets between 10 Earth masses and 1,000 Earth masses, so about 3 Jupiter masses. The terrestrial planets, the planets of the solar system, they would basically be all here at 0. They have very low eccentricity. Not so in the exoplanets. Exoplanets can often have very high eccentricities. So this is very different also from the solar system. And this is a similar plot. In the solar system, again, the equator of the sun and the plane of the ecliptic plane are more or less aligned. Not exactly, there is a certain offset. But if we go, we measure how the planes, the orbital planes of extrasolar planets compare to the equatorial plane of their host stars, we can see that at least for the hotter stars, there are planets which do not at all orbit the planet more or less in the equatorial plane of the star, but they go sometimes even retrograde or like that, also on a polar orbit. This is also something which is completely different from the solar system. And if you think of what we talked about at the beginning, we said, okay, we have this infall and we have a dominant angular momentum vector. This is a very surprising result, why they are out of the plane. And it is typically thought that both these results, here with the high eccentricities and with these high inclinations, are a consequence of gravitational interaction in this extrasolar system. So our solar system seems to be special in the sense that no strong dynamical interaction have happened. And in these other systems, this was much more violent. Again, if you have an eccentric, a giant planet, the stability of terrestrial planets is of course difficult. So this is very different too. Good. This was a very short overview of some of the most important observations, this diversity on the observation side. Let's see, can we somehow try to simulate and to understand where all this diversity is coming from? And this is something I've done in quite some time now, is to start from the following hypothesis. We have seen all this data on the end products, the exoplanets. But in the last years, there was also kind of almost a revolution, I would say, when it comes to the initial conditions. What are the properties of the protoplanetary disk? A few years, we didn't know much about them neither. But now we have these fascinating images. This is from ALMA, this is in Chile, it's in 2 millimeter. You can see here is the host star, and this would be a protoplanetary disk. I think the size is maybe also on the order of maybe 100 AU. This is another example. This is now a protoplanetary disk seen from the side. What you can see here, the star would here be in the middle. Then it irradiates the upper layers of its disks. This gives this flare structure. This here is a jet which is ejected by the young star. Here we have more observations of a number of disks. These are 2 millimeter observation, which give us the distribution of small dust in these disks. And what you can see alone, only just from these images, this here, but also comparing this, that we also have a very large diversity in these disks. So, and what we can do, or what we have started to do, is to determine distributions of these properties of the disks. And the hypothesis is now, of course, that the diversity that we observe in the planets is just the consequence of the diversity in the initial conditions. And what we then start to wonder is whether we can reproduce this diversity if we take a theoretical model, we feed it with a number of initial conditions which have a large diversity, and we want to see if we get a synthetic population of planets, so one formed in our computer code, which has a similar properties as the actual population of extrasolar planets. This is called population synthesis. This is something which is known, let's say, for stellar population synthesis. So people take an ensemble of stars, they look, let's say, they put them together, they follow their evolution, they see what kind of, let's say, luminosity distribution we get for galaxies. Do we get rather a red galaxy or blue? And this is something that is now applied also to extrasolar planets. Good. So what is the principle in this population synthesis? The most important part is here a global formation model. Global means that it is an end-to-end model. So we can put into it the properties of the disk, and what it predicts us is then the outcome, the properties of the planet. So this here a miracle occurs that sits in this part there. Then the second one are initial conditions, probability distributions from observations like the masses of this protoplanetary disk, the lifetimes and so on. And then what we can do is to run this model on a computer or a supercomputer and do it many, many times so that we get a synthetic population of planets. Then in the next step, you want to apply an observation detection bias, because we said before, okay, we cannot detect all planets nowadays, so we need to take that into account also when dealing with the synthetic population. And then the observed population comes in, and now we can make a comparison. We can see, can we reproduce the observed statistic, the mass distribution, semi-major axis distribution, and so on. And from what we saw before, that the original model we were talking about, just inspired from the solar system, would certainly fail at this point because it could not reproduce the observation of the extrasolar planets. And this is actually still the case, but this is not really this is not a problem, because this points out where we have a deficit in our understanding of the physics which are going on. So what you want to do is to go back, try to understand where these differences are arising from, go back to your theoretical model, and then improve it. And maybe at some point you get something which is at least similar. And then you can do something which is in the context of, let's say, planning missions or so, is quite interesting. You can make predictions about what you could detect if you improve, say, your detection capabilities by a factor of 10 or something like that. So this is also used by space agencies to make some estimates. Good. Let's talk a little bit more about this diversity. The first one in the diversity in the protoplanetary disks are the disk lifetimes. How long do these disks stay? This is shown here. We have as a function of the time, we have the fraction of stars, if we look at young clusters, which have still a protoplanetary disk. And what we see is that this fraction of stars, disappears on a time scale of about, the mean is maybe 3 million years. And this means that if we want to form a giant planet, we need to form it within this time scale. The second one are the masses. How much mass do we have to build our planets? And this is shown here. This is again a distribution, and the typical masses are something like between 1% and maybe 10% of the mass of the sun. So this is our initial material of gas we can use to form the planets. And second, the dust masses, this is shown here. So how many solids do we have here? We can measure what is the dust to gas ratio in stars. And here we see that we have something between maybe 10 and 1,000 Earth masses as building blocks to start with. And these are the probability distribution we then put into our population synthesis code and look what kind of outcome we get. Good. Now we come to the main part. We have seen, okay, these observation predictions. We have seen how we can set up these theoretical models. And let's try to understand first what has happened, what has gone wrong here, this close-in planets. So for that, we need to first understand how people have constructed models before we had all these nice direct images and observation of protoplanetary disk. At this time, people only had the structure of the solar system nowadays. So what they needed to do is to kind of re-engineer how the protoplanetary disk may look like given what we observe nowadays. And the idea was basically very simple. This was Schilling who did that. He just said, okay, I take the planets of the solar system, I spread their material so that we just fill the solar system, so that between the orbits, we spread the material that we have, and I look how much material there was. First, you just take, let's say for the Earth, you take the silicate, the iron, you spread it, and then you said, aha, okay, but originally there was also gas, so you add the gas to it so that you have the same composition as we have nowadays in the sun, and this is then what you see. This is a prediction. How was the surface density of the gas, so how much grams per centimeter squared of hydrogen and helium we had as a function of the distance in AU, and this was then a similar plot here, the surface density here of the rocks, and here of the rocks and the ices. And what they found was that it followed more or less R minus 3/2 dependency. So the surface density is decreasing towards the larger distances. A very important point is this jump here. This is nothing else than that. This is the snow line. In a protoplanetary disk, the inner parts are hotter because we have first the irradiation from the host star, and second, since the gas is accreting onto the star, it is liberating its gravitational potential energy, and this heats up the disk, and this needs to be irradiated, and this makes that we think that there is a similar snow line also in disks or something like that, and this is actually something which has been observed just I think this year was the first observation. So what we see here, that the condensation sequence, the temperature where the different building blocks are either in the solid or in the gaseous phase, has important consequence on the availabilities of building blocks in the solar system. So we have now derived from the setup of the planets nowadays in the solar system how the distribution of the building blocks maybe looked like in the beginning. And now we can take another step. Let's assume that we have here the sun. This is a planet which will be growing. This is proto-Jupiter at 5 AU, and we surround it by a sea of small objects, planetesimals. And we just let it grow and see how it accretes. And we will notice something, maybe if we let it run. So we integrate the orbits of the small bodies under the influence of the sun and of growing Jupiter. And what you see here is that Jupiter has now accreted all the planetesimals in a certain annulus. This annulus is very important. This annulus is the so-called feeding zone. This is the place from where a planet can accrete. Because of the solar gravity, there is a certain place around the orbit, it's a multiple of the so-called Hill sphere, where a planet can accrete. So Jupiter cannot accrete, or any other planet cannot accrete planetesimals from the entire disk, but only from a certain part of the disk. And this is shown here. If the planet does not move around, and also if the planetesimals do not move around, a planet can grow locally only to a certain mass. This mass is the so-called isolation mass. And this is plotted here. So again, semi-major axis, and here this isolation mass for different surface densities. This would be this minimum mass solar nebula, and this would be 4 times more what we have solids nowadays in the solar system. And what you can see here, if we go to small distances, then this isolation mass is very, very small. So it's just, if we take the minimum mass solar nebula, it's 0.009 Earth masses. Or even if we increase it, it's still very, very small. So this means that in this, if we look at the budget of mass that we have, the amount to which, or the mass to which a planet can grow locally, close to the star, is extremely small. So there's very little mass at these small distances. And it's especially much less than about 5 to 10 Earth masses, which we need to form a giant planet. We come to that later on. So, and from here comes this theoretical prediction from the classical models that giant planets can only exist outside of a few AU. This jump here is again where the surface density increases because of the condensation of water. So this was the classical idea why we have this outcome, that we have large planets only at large distances and small planets only closer in. This is the theoretical origin of that. Let me quickly say something to the theory that I'm using to explain the formation of Jupiter mass planets. This is the core accretion theory. There it is seen, the formation of a Jupiter mass planet is seen as a two-step process. First, accretion of a solid core, 5 to 10 Earth masses, which has such a strong gravity that the gas surrounding it collapses onto this core. This is the core accretion theorem, and this is the mostly used theory to explain the formation of Jovian mass planets. Let's look at that, saying that we don't have close-in mass planets using our population synthesis model. So what we do now, we vary the initial conditions to our theoretical formation model, and we look what kind of planets that we predict, still assuming that planets form just in situ, at the place without moving around. And this is the result. And what you can see, we have semi-major axis versus mass. We do get here from the theoretical model, we do get giant planets, but again, the prediction is that they are all outside of a few AU. So it is not the diversity of the initial conditions that gives this result that we cannot have giant planets close in. This doesn't help. It tells us that we are actually missing some physical mechanism. And this was actually noticed well before that there could be something which changes our idea that planets form where they are now. And this is the concept of orbital migration. So it was proposed already in the 80s by Goldrake and Tremaine that if we have a planet or a protoplanet which is embedded in the gas disk, it will of course gravitationally interact with this gas disk. And this leads to an exchange of angular momentum. And typically the angular momentum exchange is such that the planet loses angular momentum and moves towards the star. And this was then actually also taken into account. This is the detection paper of 51 Pegasi b, this first hot Jupiter, and they of course had read this theory about orbital migration. In the solar system, it seems as there was no such strong orbital migration. And this is now the tricky question, why? This is highly debated because you'll see also later a little bit, orbital migration principle is predicted to be extremely efficient. The most widely accepted theories nowadays is that in the solar system, you have a little bit of special situation. We have a more massive planet closer in, Jupiter, and a less massive planet, giant planet, a little bit further out. And we can show, and this is understandable also from theoretical arguments, that if we have this special situation of these two different masses, then the migration behavior is changed. Usually, it is always towards the star. But if we have this special situation, then the torques are different, and this makes that this migration is not as efficient or maybe even outward. This is probably the explanation. So this is to show you a little bit how we can simulate that. This is a hydrodynamic simulation. So we take a gas disk around the star, and we put into a planet, and we just calculate all the forces, the exchange of basically this Newton's law. And this is what we see. So here we have the star, here we have our protoplanet. This is the fixed reference frame. You see how the star, how the planet is going around its star. And what you see is these kind of density waves, which are launched in the gas disk. And these density waves, they have the influence, those which are outside, they pull the planet back, which means it loses angular momentum and migrates inward, while we have the inner here, the inner pull, which is a forward pull and which causes outward migration. And what matters in the end is the net torque. So the differences between these two. And this is a little bit the reason why migration is a very, very tricky business. Because to first order, this is symmetric, you can see. And this means that the torques would balance, but they don't balance exactly. And it is the difference between the two which causes then the orbital migration. And this is difficult to simulate. What happens if we take that into account in our theoretical model? So we now go again to our population synthesis model, but in contrast to before, we include the effect of orbital migration. What we have here, what you will see is an animation. We start with very small objects, then they grow by accreting planetesimals like we saw in the other animation, and they can also accrete gas, and they undergo orbital migration. This is what you find. So you can see that these objects, they are growing, but at the same time, they are also migrating closer to their star. So if we take this effect into account, then we get a lot actually of close-in planets like the hot Jupiters that we observed. So the lessons learned here was clearly that if we don't include orbital migration, we cannot predict the observations. However, this is the nicer part of the story. The less nice part of the story is shown here. What I didn't mention in the plot before was that there we had to reduce the migration rate by about the factor 10 to 100. And what happens if we don't reduce it? This is shown here. Now the planets grow, but the migration is so efficient that all these objects, before they can grow to a big size, this is the mass of Saturn, and we had all the observations up here. What happens? They just fall into their host star. So, yeah, it's a good thing, but too much of the good thing kills the good thing. And this is the current situation we are facing. And there are a number of ideas, relatively complicated physics, a lot with thermodynamics, which could maybe explain that we are closer to reproducing the observation, but we can still by far not explain it completely. Good. This was the first test. Let's go to the second one. This is the absence of planets at large semi-major axis, so outside of a maybe 30 AU. And the subject that we touch in this context is the timescale of planetary growth. Because what we've seen already before, if you remember the mass distance diagram, we had all these directly imaged planets at large distances. This one is an example of that. That's HR 8799. I would guess it's the most famous directly imaged extrasolar planet system. It's a crazy system. It consists of 4 giant planets with massive things. 7 Jupiter masses, again 7, 5. So really a lot of mass in these planets. And look at the semi-major axis, 15 to 70 AU. So they are very far from their star, much further than what we had expected from the solar system. So this is again it's probably the most important example that shows that also the theory we had from the solar system does not really work. And this is a very nice system because we have now very good observations of it. This is an animation where it was observed over several years. And what you can see here is the orbital motion of these planets, the self-luminous planets around the host star. So you can see how it moves in time. What is interesting is that these planets are probably in resonances. So they are in mean motion resonances, meaning that if one object goes around the star, I don't know the exact numbers, but say one goes around twice, then the other goes around 3 times or something like that. So this is a very fascinating system. And let's try to understand why in the classical theory we would have said that such an object cannot exist. For that, we quickly need to think a little bit how planets grow, how they accrete. And this is what you can think is the following. Let's assume that we are in our protoplanetary disk. We have one bigger object, our protoplanet, and there is a lot of small background planetesimals. This big object moves through these planetesimals with a certain relative velocity. This means that, and let's assume further, that our planet has a certain cross-section, so that everything which it sweeps is just accreted onto the planet. This is what happens then. The mass increment it has is just how much mass we have here. And this is the volume of the cylinder times the density of the planets in space of planetesimals inside here. And this is this equation. So the amount that the protoplanet is growing is the density of planetesimals in this volume times the volume. And what is the size of the cylinder? It's the cross-section sigma times its length. And the length is, of course, nothing else than the velocity times the time we are looking at. And from that, we get actually one of the most famous equations when it comes to planetary growth. This is the so-called Savaronov equation. It tells us how planets accrete solids. What we are now interested in is how this equation behaves as a function of distance. Let's have a look. So the cross-section of the planet will not depend on the distance. But here we have the density of the planetesimals. And remember, we had learned before that this density is decreasing if we go further away. So this is decreasing if we go further away. What about the velocity? The relative velocity scales with the Keplerian velocity. The Keplerian velocity is shown here. It's the gravity constant times the mass of the star divided by the distance to the star. So if this becomes big, then this equation becomes small. So both these terms are becoming smaller as we move further out, meaning that if we go further, still further away from the star, the slower and slower we are going to accrete the solids. And this means that we can grow planets only within a certain distance from the star. And this is shown here in the simulation. What do we have here? We have the distance in AU, and here we have the mass to which a planet can grow. Let's look at the very beginning, 0.1 million year. You see, this line here is where to which mass our planets have grown. So here we have seen in the inner system, we have grown a little bit, and we have again here a little bit of growth outside again of our ice line. This is again this isolation mass that we encountered earlier on. Let's go to 1 million here. Now our growth wave has traveled outwards. So we grow at close in distances very fast, and it takes longer to grow at large distances. Let's move again forward, 3 million years and 10 million years. We saw before that 10 million years is about the maximum time that we have in order to, because afterwards our protoplanetary disk is gone. So, and if you see, the largest distance to which we were able to grow something is about 10 AU. Nothing has grown outside. And this is the physical explanation why in the classical theory it was predicted that no planets should exist outside of a few 10 AU. So again, here we have, in principle, it seems something like a very sensible prediction, but which in observation in the end didn't prevail. And we can also make a test again with population synthesis here for one solar mass host stars or also for more massive stars. But you see in any case, there is not much outside of 20 AU. So this tells us again, also here we miss some physical effect. Something is different. And what is probably the explanation for these planets at very large distances is that they formed in a completely different way than the planets, the giant planets in our own solar system. Because what we are dealing with now was this core accretion theorem. Remember, we first need to build a solid core, then we can accrete the gas. But this is not the only possibility how we may form giant planets. The other one is shown here. This is the so-called gravitational instability or direct collapse model. What happens here is that the gas disk becomes unstable due to its own gravity without having a solid core or something like that. This is shown here. And this can happen also at very large distances. Actually, it's even favored to happen at large distances. And there are two criteria when it occurs. The first is the tumor criterion. This is the same criterion which you can also use to see whether we have spiral waves in a galaxy. So it tells you whether a rotating disk is stable or not. And the second one is the cooling criterion, because imagine that we have some gas in a protoplanetary disk which becomes unstable. It wants to contract under its own gravity. But if you try to, let's say, pump up a tire, then it will heat up. And exactly the same happens if you try to compress this gas, it will heat up, and this will make a pressure, so it cannot contract. If you want it to contract, it must be able to cool, because then it can continue to become denser and denser. And this is the second criterion. And a way of looking into that is, of course, to simulate this. This is a simulation of such an unstable disk. We have here in the middle the star. The color is color coding the surface density of the gas, and let's see what happens here. So you can see that we have this kind of spiral waves. We have this quite similar of what we now actually observe. Let's see what happens further. Yes, we have now some nice pattern here, and at some points we have these over densities. these overdensities, if they are strong enough like here, they can develop into bound clumps. And these bound clumps, what they do, here we have several of them, they will also interact gravitationally with each other. And some of them are like this poor guy, they're undergoing this migration we were talking before, and they get too close to the star where they are sheared away by the Keplerian shear, because when you're closer, you go faster than you go when you're further out. This means that you disrupt your clump. So you can see that here we have a very wild system, and it is thought that maybe in HR 879 such a similar process has happened. Here in this simulation, I think that in the end, everything falls onto the star. And this is, so also here, maybe the idea is right, but if you then want to make it qualitative, it's not that simple. Yeah, right now we are just back with, we're just left with this guy and this one here. Let's see what they do. So they're interacting. Yeah. Okay. Oh, this was sheared apart. So there's one hope. Okay, I already told you that they will not survive. But you can see, so this is also a very violent process compared to what we think what has happened in the solar system. In this case, the object gets also in the end fully disrupted. So there is nothing left. But there are, of course, also simulations where we can end up then with a bound clump. Good. So here, the explanation was that inspired from the structure in the solar system, we developed this nice core accretion theory. But there are other theories that also can lead to, or other mechanisms that can also lead to the formation of giant planets. So let's go to the last point here. This is the different planetary types. So we have seen that in the solar system, we have this relatively well separated compositions, the rocky planets, the ice giants, and the gas giants. And for this we can use on another plot, which is also very important. This is now the mass radius plot. So what we have here, Venus, Earth, Uranus and Neptune, Saturn and Jupiter. And you can see that again here they group in these three groups. Here we have additionally lines which show theoretical predictions how the radius of a planet looks like for a given composition. So this would be the mass radius relation for a composition like the Earth, so 2/3 silicate, 1/3 iron. Here, this would be the line for a pure ice planet. You can see Earth and Venus, of course, fall on this line. Uranus and Neptune are a little bit above it. This means that they contain an additional light component. And this is, of course, as we know, hydrogen and helium. And this blue line is finally the mass radius relation you expect for an object which is mostly hydrogen, helium, and maybe 10% other objects. So this is quite well understood in the solar system. But let's look again the extrasolar planets. And what you can see is that we have, as I mentioned already, a real continuum. We have here, okay, this is a bias. Here we haven't detected much of these planets yet. But here you see that we have at each mass, we have a wide range of different radii. You see here at 10 Earth mass, for example, there are some objects which seem to have a rocky composition, but also some which have a very large radius. So they seem to contain a lot of hydrogen helium. This is very interesting because from this mass radius relation, this allows us to make a first geophysical characterization of these planets. And this has been done, and especially in this mass range, which we don't have in the solar system. This is another speciality. In the solar system, we have one Earth mass, the Earth, and then the next planet is 14 Earth masses, Uranus. There's a big gap by one order of magnitude. This is not at all like that in extrasolar planets. Actually, planets in this intermediate mass range are the most common planets, it seems, around other stars. And then we immediately wonder, but are these now bigger versions of the Earth, or are they smaller versions of Uranus and Neptune? And one way to answer that is to have a look at this mass, this kind of plot. So again, we have the planet mass versus the radius, and then to compare them with the hydrogen helium content, with the radius, to infer the hydrogen helium content. And this is what is done here. So here people have done this kind of study. They looked at the mass and the radius, and they looked, in order to reproduce that, how much gas do we need to add? And this is shown here. So we have mass, and this is how much hydrogen helium we have. We have low masses here at less, let's say less than 10 Earth mass, and then we have this increase. And this is something we also can use to improve our understanding how these different planet types come about. Why do some planets accrete a lot of gas, and why do other planets not accrete a lot of gas? And also here we can make some theoretical considerations. How do planets accrete gas? And this you can imagine in the following way. Let's say we have one of these protoplanets, maybe between 5 and 10 Earth masses, embedded in the protoplanetary disk. Due to the gravity, it will attract a little bit of gas. But as we said before, if we compress it, it will heat up and we stop accreting more gas. And only if the gas can cool a little bit, then we will be able to accrete more gas. This cooling is called the so-called Kelvin-Helmholtz timescale. So how quickly can the planet get rid of its heat? And this is shown in this equation. So we can say the accretion rate of gas is the mass of the planet divided by this time scale to get rid of the heat. And this we can calculate what it is. And what we find is the following expression. So this is in years. This is the mass of the planet. So it's mass minus 2.5. This means that if we increase the mass of the protoplanetary core, then this time scale goes down a lot. So meaning that we can quickly accrete the gas. And if you put in some numbers, then you see that here we get a time scale of about 100 million years for a 1 Earth mass planet, meaning that we cannot accrete a lot of gas, because remember, the typical lifetime of a protoplanetary disk is only between 1 and 10 million years. And here it takes 100 million years to accrete a lot of gas. If you go to 5 Earth masses, you see, okay, this time scale to accrete the gas goes down to about 2 million years, meaning that we can accrete a little bit of gas. And if you then go to 10 Earth masses, then you see this time scale is just a third of a million years or something like that. This is much less than the typical lifetime of a disk, meaning that we can accrete a lot of gas if we can build up a core of 10 Earth masses. And this was the criterion that we used before in the core accretion theory, that in order to form a giant planet, we need to create a core of about 10 Earth masses. But let me point out another thing here. This is the small parameter kappa. Kappa stands for the opacity. So for how well radiation can be transported through the envelope, through the atmosphere of this planet. If the opacity is high, so if it's difficult for the radiation to go out, then of course this time scale increases. And now we can do something very interesting, because what we can now do is try to have an understanding of what this kappa could be by comparing theoretical predictions for the amount of gas a planet can have given a certain kappa here. And how can we do that? We have seen before that if a planet of a given mass has a lot of hydrogen helium, then its radius will of course be bigger, because it can accrete more gas. And I will, in the interest of time, I see I'm a little bit behind time, I will skip here a figure, so then we are soon done. So what I said, what we can now use is the observation of the mass radius diagram of the exoplanets to understand something about this opacity in the protoplanetary atmospheres. Namely in the following way. Let's make, again, one of our population synthesis and assume that this grain opacity, I didn't mention that, this opacity is mostly due to small grains, clouds, if you will, which are suspended in these protoplanetary atmospheres. It's like fog. In a foggy day, the opacity is very high. You cannot see very far because the radiation is propagating only, there's a lot of scattering. So this is the same. Let's assume here in the first case, you have very low opacity. And what you can see, I'm sorry, it's a little bit small, the figure, but this here, these points are observations, and in colors, we have the theoretical prediction. And what you can see is that if we assume very low opacity, then our theoretical predicted radii are typically bigger than the observed ones, meaning that our model predicts that we can accrete too much gas compared to the reality. We can also do the opposite. We can assume that we have very high opacities. And what you now see is that our theoretically predicted radii are smaller than what is observed. This tells us that this opacity is too high in compared to reality. And finally, we can try to build models and see, okay, if we use a certain model for the grain dynamics, how does this opacity come into existence? Then we can more or less reproduce this observation. So what I've shown you with that is that thanks to this laboratory, we can try to link microphysical processes like the grain growth with the observations. And this is also something I think very interesting, because before this was not possible. And what you can also see is that because the opacities that is found here in this nominal model are typically relatively low, this means that also low mass planets can accrete hydrogen helium. And this is probably the explanation. While in the extrasolar planets, you have also low mass planets which can accrete hydrogen helium, and not so that we don't have this real distinction in these different planetary types. Good. Let me come to the last part, the outlook and the conclusions. So something that you certainly remember at the beginning was that we said that it's very difficult to observe planet formation as it happens. And I already showed you an example here, how nowadays, or very recently, this has really changed. This here is an image of a protoplanetary disk. Here in the middle would be the star. And what it was found here is an observation in infrared that here at, I don't remember the exact distance, but a few 10 AU or something like that, there is a very strong source in this protoplanetary disk. And very likely, this is a forming giant planet, which is really observed in the process of formation. This here is a similar observation. This is the observation here of H alpha. H alpha is a line which comes into existence if hydrogen recombinates. And what is here happening probably is that we have a forming giant planet onto which gas is falling with high velocity at free fall speed. It's hitting the surface of the planet, getting ionized, recombines, and emits this H alpha. So we have direct observation of planet formation as it occurs. And this is, I think, really something very fascinating, because what it will mean that we are now able to see planets at different moments in their life. So very young, then the very old ones, like we knew before, but also intermediate times at intermediate ages. And then I see for the future, or I hope that we can develop an understanding of planet formation a little bit like for the stars. This is the Hertzsprung-Russell diagram, where you see the different stages through which stars are going through their life. This is the track of the sun with the main sequence where it's now. It's become a giant and a white dwarf. This here would be during the formation. And this is, of course, very nice, because we can here associate all these different parts with the track of a planet during its, of a star, excuse me, during its own life. For planets, this was not possible until now, because we only observed old planets, basically. But what should be possible in the future is to do something similar also for the planets, because as I showed you already, these two examples before, but especially if we look into the future, there are now a number of new instruments and space missions which will allow to observe, this is a theoretical prediction, how such a track of a planet now looks like in the same way in the Hertzsprung-Russell diagram of planets. This is a theoretical prediction, and that we can then compare them with observations. So here the very early phases when the planets are growing, then here this at a little bit a later stage, or this stage here where we have this H alpha emission, then shortly after formation, like here in this directly imaged planet, and then finally here at the old ages like Jupiter. So because if we can construct observationally such a diagram for the planets, we can understand a lot of what about is going on, similarly as it was possible when the Hertzsprung-Russell diagram was built. Thank you very much.
Thanks a lot, Christoph, for this fascinating talk. I'm quite sure there are some questions. If not, I start with the first one.
Yes.
Is the name already given for this diagram, or would this be the Mordasini diagram then?
No, actually, there's no name. It's funny. I think it's actually, I think, true to say that no one has really thought of it yet, because this is an important point. The field is really observationally driven, and this kind of possibility to observe this early phases is really, it's 2 or 3 years, and now only theoreticians are starting to digest and to see what could we do with it. So yes, this is in that sense something new.
Okay, this would also have been a question. So it's really at the moment still observationally driven. Yes. So the theoreticians are hunting, so to say, to catch up with what the observers provide you, right?
Most of the time. Sometimes there is also the opposite. For example, for TRAPPIST, there was a prediction that there will be an additional planet, and this was now confirmed observationally. But this is very rare. Typically, it's the opposite. Yes. Yes, this is mostly it's sphere instrument at the VLT. I'm a member of the instrument consortium, so this is one of these direct imaging instruments. There is a competition instrument, GPI. This is from the American consortium. The two came online almost at the same time. These are adaptive optics direct imaging instruments. Then for the disk, it's also ALMA, the ALMA Observatory submillimeter.
I remember a Pricey talk by Willy Benz 18 years ago.
Oh.
You were probably in Optical, where he talked about the growth of planets.
Yes.
It's well understood how the little brains form, and it's well understood how larger planets form from protoplanets once they can attract each other.
That's right. Yep.
But the gap in between was back then one of these miracles.
Yes, that's right.
How has this?
Yes, it's a very interesting question. There has indeed been, although it's still debated, but we think that there has been significant progress in that. And this is the following. So what Rudi mentioned is that if we have small grains or maybe centimeter or so, they can stick well together. But try to make two rocks stick. They don't stick. Only if you're big enough to have gravity, then again they stick. And what is the current theory is the following. Namely, that we have turbulent disks. In these turbulent disks, you can have a concentration of dust in a local vortex. And this concentration can become so high that the dust becomes self-gravitational. We talked about the gravitational instability of gas. Actually, exactly the same Tumru criterion can also be used in a modified way to see when a disk of dust becomes unstable. And numerical simulation have shown that this concentration in these turbulent eddies can become so high that the dust collapses under its own gravity. And what then happens is that you jump from, say, centimeter big objects directly to several 10 kilometers or something like that. This is the understanding. This was, I think, one of the most important progresses in the last 18 years.
I wonder, you have Saturn's rings.
Yes.
Why don't they accrete into bigger moons?
I think, yes, the reason is that this is inside of the Roche limit. So this means that they would, if they try to accrete, they get torn apart by the differential gravity. For each object, there is a distance where basically the gravitational pull on your feet is different and your head, and it tears you apart. This is the Roche limit. So they cannot grow bigger. They can exist at the small scales because there are the Festkörperkräfte which keep it together. But if you try to grow and it's just gravity which holds you together, then you get torn away apart by the differential gravity. You're basically too close to Saturn in order to grow.
But some objects have been found.
Yes, that's true, but they are relatively small. Bigger objects, they cannot exist. Actually, there is a very interesting theory how the moons further out form. There, the idea is that these rings were more massive originally, and they were spreading viscously, so they're getting bigger. And once the material is getting out of this limit, a moon forms, which then leads to the formation of one of Saturn's moons. This is a theory to explain the existence of moons for Saturn.
What about the gravitational instability?
Yes.
In the gas, would you also expect to have binaries from this was a scenario in the solar system?
Yes. Yes. The Tumor criterion, in order to become unstable, you need a cold disk because then you don't have much pressure force, and you need a massive disk because then you have strong gravity. And if you then see under what circumstances a disk can become unstable, it happens in massive disks, 10–20% of the solar mass. And this is one of the biggest challenges actually of this theory, because what happens typically, you form this clump. The initial mass of the clump might be indeed Jupiter mass-like you wish, but you don't stop accreting once you have formed your clump. And most of the time, it seems that these objects rather continue to grow to become binary stars. They become much more massive than planets. So it seems that there's maybe a small parameter space where you can still have the instability, but still not become a binary star.
Would you also form binary planets?
Binary planets, oh, excuse me. Oh, binary planets.
In some simulations, I've seen that binary planets trans-Neptunian objects were formed.
Yes, that's true.
I don't know the initial conditions, I don't know how they compare.
I've not seen any simulation showing that. Yes, I guess it has to do with stability issues, but I wouldn't exclude it necessarily in any case. But I'm not aware of that, I have to say.
They may have to be far out to not become destabilized. Huh?
Yes.
Further questions? Very short and probably irrelevant question is the current extrasolar planet.
Yes.
I don't like it because all planets are extrasolar. Intrasolar planets are not.
Yeah. What should I say? Yes.
You have a better term?
No. Well, we should probably ask the International Astronomical Union. They have a special committee to discuss these things. I mean, as you know, probably recently there were this naming campaign at least. So they have now names at least.
You showed us the big diversity of extrasolar or extrasolar systems.
Yes.
And quite different from what we have here.
Yeah.
So I wonder whether this reflects the anthropic principle that we can only observe something which allows life.
I think to some extent, yes. We talked about these very eccentric giant planets. They, of course, sweep large parts of their system. They get close to the star, they go very far away. Stable orbits at 1 AU in the habitable zone are then not possible. So I think there is indeed a certain selection process. On the other hand, I mean, you could think of very exotic habitats. Let's say you could think of a moon which is in orbit around a giant planet which gets tidally heated such that you can have liquid water like on Europa. This could also be a habitat. So, but maybe life, like here on Earth, there could be a certain bias towards system like our system, yes.
There was a question.
I have a question about observational techniques.
Yeah.
So if I were to ask you to look ahead, say 20, 30, 50 years ahead, where will the progress be made? Will it continue to be a fusion of ground-based and space-based techniques, or how do you think it will go in the longer, or in the midterm?
I mean, JWST is of course on the horizon. This is now when it comes to the detailed observation of a handful of particularly interesting systems. There, of course, this will have a prime role, especially for the observation of atmospheres, atmospheric composition. On the other hand, getting time on JWST to make some survey, no. So I think indeed it is the combination of the two. For example, for much of this radial velocity work, the 4-meter class telescopes has proven to be very important. I mean, many people thought, okay, we need 8-meter class telescopes, but this is not the final answer. So also this kind of if you read, because I mean, a lot of the understanding here comes from statistics. This is probably really one of the most important things. And this, I guess, will continue that we have that. There are a number of missions planned. Plato, for example, it will be very important, especially we talked about this possibility to observe for the first time planets in time. Plato will do a lot of astroseismology so that you can date the age of the planets. This will be, I think, something very fascinating.
My question was a little bit beyond your work, the next step.
Oh.
Once you can probably analyze extrasolar planetary atmospheres, what would be the best signature for life? I mean, which spectral line do you look for methane?
Yeah.
Do you need water and methane?
Yes, so it is very tricky. I mean, classically, people were saying, okay, ozone and oxygen, because, you know, oxygen is a very reactive gas. I don't know if we would switch off photosynthesis. I forgot the exact number, but it wouldn't take on astronomical or geophysical scales long until everything is built into oxides of rocks, of things. So it's a relatively fast process. So if you detect large amounts of that, this is typically seen, was seen, I have to say, as a biomarker. Unfortunately, imagine you have a planet which consists of water, mostly, could be if it migrated from outside of the ice line close to the star. Depending on the regime where it is, the water can be dissociated and you lose a lot of hydrogen and you're left with a lot of oxygen. This would be an abiotic process. So probably what people say is that you want to look for two gases which are usually not from abiotic processes existing at the same time, like methane and oxygen, because usually you don't find them. They are I mean, if you make a Gibbs potential and you minimize it, you won't have the two gases at the same time, just from physics or chemistry. So this is probably a way to search for.
When do you expect that you will be able to read the photon counting? That's what it's going to be, I guess, more or less. Or...
I mean, JWST people is probably still not, it's maybe not yet possible, but then there are the next successors. They should probably be able to detect these things. So NASA has this HubX, I think, how is it called? I forgot, but it's just the next generation of space telescopes.
Is there any last question? If not, as you are probably all hungry and thirsty,
That's what they would have said.
that's his usual saying. I would like to close here. Thank first of all again Christoph Mordasini for this great talk, and I would also like to quickly announce, of course, the next talk. So we would be glad to see many of you again on 10th of May. So you may have seen these nice artist machines that are being produced. So on 10th of May, we will have Kurt Lambeck. He is Johannes Geis Fellow visiting ISSI during that time with the title Return to Planet Earth, Understanding the Earth from Geodetic Space Observations. So it's a big jump from extrasolar planets or extrasolar system planets back to the planet Earth, but I'm sure it's worth coming again, and I'm looking forward to see you all here in 2 months again. Thanks a lot.